9 on the human mind, mathematics, and the universe. The two questions: does mathematics have an existence independent of the human mind, and why do mathematical concepts have applicability far beyond the context in which they have originally been developed, are related in complex ways. Still, to simplify the discussion, I will, em- I will attempt to address them sequentially. If you may wonder where modern day mathematicians stand on the question of mathematics as a discovery of an invention, here is how mathematicians Philip Davis and Raven Hicks describe the situation in their wonderful book The Mathematical Experience. Most writers on the subject seem to agree that the typical working mathematician is a Platonist, views mathematics as discovery on weekdays and a formalist view mathematics as invention on Sundays. That is, when he is doing mathematics, he confessed that he is dealing with an objective reality whose properties he is attempting to determine. But then, when challenged to give a philosophical account of this reality, he finds it easiest to pretend that he does not believe in it after all, other than being tempted to substitute he or she for he everywhere. To reflect the changing mathematical demographics, I have the impression that this characterization continues to be true for many present-day mathematicians and theoretical physicists. Nevertheless, some 20th century mathematicians did take a strong position on one side or the other. Here representing the Platonic point of view is G.H. Hardy in A Mathematician's Apology. For me, I suppose, for most mathematicians, there is another reality, which I will call mathematical reality, and there is no sort of agreement about the nature of mathematical reality among either mathematicians or philosophers. Some hold that it is mental and that in some sense we construct it, others that it is considered and independent for us. A man who could give a convincing account of mathematical reality would have solved very many of the most difficult problems of metaphysics. If he could include physical reality in his account, he would have solved them all. I should not wish to argue any of these questions here, even if I were competent to do so, but I will state my own position dogmatically in order to avoid minor misapprehensions. I believe that mathematical reality lies outside us, that our function is to discover or to observe it, and that the theorems which we approve and which we describe grandiloquently as our creations are simply our notes of observations. This view has been held in one form or another by many philosophers of high reputation from Plato onwards, and I shall use the language which is natural to men who holds it. Mathematicians Edward Casimir 1870 until 1955 and James Newman 1907 until 66 express precisely the opposite of perspective in mathematics and the imagination. That mathematics enjoys a prestige unequaled by any other applied or purposive thinking is not surprising. It has made possible so many advances in the sciences. It is at once so it is at once so indispensable in practical effects, and so easily the masterpiece of pure abstraction that the recognition of its preeminence among men's intellectual achievements is no more than its due. In spite of this preeminence, the first significant appraisal of mathematics was occasioned only recently by the advent of non-Archimedean and four-dimensional geometry. That is not to say that the advances made by the calculus, the theory of probability, the arithmetic of the infinite, topology, and the other subjects we have discussed are to be minimized. Each one has wider mathematics, are deepened its meaning as well as our comprehension of the physical universe. Yet none has contributed to mathematical introspection, to the knowledge of the relation of the parts of mathematics to one another, and to hold as much as the non-Euclidean heresies. As a result of the valiantly critical spirit which engendered the heresies, we have overcome the notion that mathematical truths have an existence independent and apart from our own minds. It is even strange to us that such a notion could ever have existed. Yet this is what Pythagoras would have taught and Descartes, along with hundreds of other great mathematicians before the 19th century. Today mathematics is unbound. It has cast off its chains. Whatever its essence, we recognize it to be as free as the mind, as prehensile and as the imagination. Non-Euclidean geometry is proof that mathematics, unlike the music of the spheres, is man's own handiwork, subject only to the limitations imposed by the laws of thought. So contrary to the precision and certitude that are the hallmark of statements in mathematics, here we have a divergence of opinions that is more typical of debates in philosophy or politics. Should we be surprised? Not really. The question of whatever mathematics is invented or discovered is actually not a question of mathematics at all. The notion of discovery implies persistence in some universe, either real or metaphysical. The concept of invention implicates the human mind, either individually or collectively. The question therefore belongs to a combination of disciplines that might involve physics, philosophy, mathematics, cognitive science, even anthropology, but it is certainly not exclusive to mathematics, at least not directly. Consequently, mathematicians may not even be the best equipped to answer this question. After all, poets who can perform magic with language are not necessarily the best linguists, and the greatest philosophers are generally not expressed in the functions of the brain. The answer to the invented or discovered question, or the answer to the invented or discovered question can therefore be gleaned only, if at all, for a careful examination of many clues deriving from a wide variety of domains. Metaphysics, physics, and cognition. Those who believe that mathematics exists in a universe that is independent of humans still fall into two different camps when it comes to identifying the nature of this universe. First, there are the true Platonists from whom mathematics dwells in the abstract, eternal world of mathematical forms. Then there are those who suggest that mathematical structures are in fact a real part of the natural world. Since I have already discussed pure Platonism and some of its philosophical shortcomings quite extensively, let me elaborate a bit on the latter perspective. The person who presents may be the most extreme and most speculative version of the mathematics as a part of the physical world. Scenario is an astrophysicist college Max Tegmark of MIT. Tegmark argues that our universe is not just described by mathematics, it is mathematics emphasis added. His argument starts when the rather uncontroversial assumption that an external physical reality exists that is independent of human beings. He then proceeds to examine what might be the nature of the ultimate theory of such a reality, what physicists refer to as the theory of everything. Since the physical world is entirely independent of humans, Tegmark maintains its description must be free of any human baggage, e.g., human language in particular. In other words, the final theory cannot include any concepts such as subatomic particles, vibrating strings, warp spacetime, or other humanly conceived constructs. From this presumed insight, Tegmark concludes that the only possible description of the cosmos is one that involves only abstract concepts and the relations among them, which he takes to be the working definition of mathematics. Tegmark's argument for a mathematical reality is certainly intriguing, and if it were true, it might have gone a long way toward solving the problem of the unreasonable effectiveness of mathematics. In a universe that is identified as mathematics, the fact that mathematics fits nature like a glove would hardly be a surprise. Unfortunately, I do not find Tegmark's line of reasoning to be extremely compelling. The leap from the system of an external reality independent of humans to the conclusion that in Tegmark's words, you must believe in what I call the mathematical universe hypothesis, that our physical reality is a mathematical structure, involves, in my opinion, a sleight of hand. When Tegmark attempts to characterize what mathematics really is, he says, to a modern logician, a mathematical structure is precisely this, a set of abstract entities with relations between them. But this modern logician is human. In other words, Tegmark never really proves that our mathematics is not invented by humans, he simply assumes it. Furthermore, as the French neurobiologist Jean-Pierre Chanjois has pointed out in response to a similar assertion, to certain physical reality for mathematical objects on a level of the natural phenomena we study in biology pose a worrisome epistemological problem, it seems to me. How can a physical state internal to our brain represent another physical state external to it? Most other attempts to place mathematical subjects squarely in the external physical reality simply rely on the effectiveness of mathematics in explaining nature as proof. This, however, assumes that no other explanation for the effectiveness of mathematics is possible, which, as I will show later, is not true. If mathematics resides neither in the spaceless and timeless Platonic in Platonic world nor in the physical world, does this mean that mathematics is entirely invented by humans? Absolutely not. In fact, I shall argue in the next section, the most of mathematics does consist of discoveries. Before going any further, however, it would be helpful to first examine some of the opinions of contemporary cognitive scientists. The reason is simple. Even if mathematics were entirely discovered, then discoveries would still have been made by human mathematicians using their brains. With the enormous progress in the cognitive sciences in recent years, it was only natural to expect that neurobiologists and psychologists will turn their attention to mathematics, in particular to the search for the foundations of mathematics in human cognition. A cursory glance at the conclusions of most cognitive scientists may initially leave you with the impression that you are witnessing an embodiment of Mark Twain's phrase, "The man with a hammer with everything looks like a nail." With small variations in emphasis, essentially all of the neuropsychologists and biologists determine that mathematics is a human invention. Upon close examination, however, you find that while the interpretation of the cognitive data is far being unambiguous, there is no question that the cognitive efforts represent a new and innovative phase in the search for the foundations of mathematics. Here a small but representative sample of the comments made by the cognitive scientists, the French neurobiologist Stanislas Dehaene, whose primary interest is in numerical cognition, concluded in his 1997 book, The Number Sense. The intuition about numbers is thus anchored deep in our brain. This position is in fact close to the fact or the intuitionists who wanted to ground all mathematics in the pure form of intuition of the natural numbers. De Heine argues that discoveries about the psychology of arithmetic confirm that numbers belong to natural objects of thought. They then categories according to which we apprehend the world. Following a separate study conducted with the Munduruku, an isolated Amazonian indigenous group, De Heine and his collaborators aided in 2006 a similar judgment about geometry. The spontaneous understanding of geometrical concepts and maps by this remote human community provides evidence that core geometrical knowledge, like basic arithmetic, is a universal constituent of the human mind. Not all cognitive scientists agree with the latter conclusions. Some point out, for instance, that the success of Munduruku in the recent geometrical study, in which they had to identify a curve among straight lines, a rectangle among squares, and a ellipse among circles, and so on, may have more to do with their visual ability to spot the odd one out, rather than with an innate geometrical knowledge. The French neurobiologist Jean-Pierre Chanchois, who engaged in a fascinating dialogue on the nature of mathematics with the mathematician of Platonic persuasion, aligned cons in conservations on minds, matter, and mathematics, provide the following observation. The reason mathematical objects have nothing to do with the sensible world has to do with their generative character, the capacity to give birth to other objects. The point that needs emphasizing here is that there exists in the brain what may be called a conscious compartment, a sort of physical space for simulation and creation of new objects. In certain respects, these new mathematical objects are like living beings. Live living beings, they are physical objects susceptible to very rapid evolution, unlike living beings, with a particular exception of viruses, they evolve in our brain. Finally, the most categorical statement in the context of invention versus discovery was made by cognitive linguist George Lakoff and psychologist Ravel Nunes in their somewhat controversial book Where Mathematics Comes From. As I have noted already in chapter 1, they pronounce, mathematics is a natural part of being human. It arises from our bodies, our brains, and our everyday experiences in the world. Lakoff and Nunez therefore speak of mathematics as arising from an embodied mind. Mathematics is a system of human concepts that makes extraordinary use of the ordinary tools of human cognition. Human beings have been responsible for the creation of mathematics, and we remain responsible for maintaining and extending it. The potter of mathematics has a human face. The cognitive scientists base their conclusions on what they regard as a compelling body of evidence from the results of numerous experiments. Some of these tests involve functional imaging studies of the brain during the performance of mathematical tasks. Others examine the math competence of infants or of hunter-gatherer groups such as the Munduruku, who were never exposed to schooling, and of people with various degrees of brain damage. Most of the researchers agree that certain mathematical capacities appear to be innate. For instance, all humans are able to tell at a glance whether they are looking at one, two, or three objects, an ability called subitizing. A very limited version of arithmetic in the form of grouping, pairing, and very simple addition and subtraction may also be innate, as is perhaps some very basic understanding of geometrical concepts Although this assertion is more controversial, neuroscientists have also identified regions in the brain, such as the angular gyrus in the left hemisphere, that appear to be crucial for juggling numbers and mathematical computations, but which are not essential for language or the working memory. According to Lakoff and Nunez, a major tool for advancement beyond these innate abilities is the construction of conceptual metaphors, though processes that translate abstract concepts into more concrete ones. For example, the conception of arithmetic is grounded in the very basic metaphor of object collection. On the other hand, Bohr's more abstract algebra of classes metaphorically link classes to members. The elaborate scenario developed by Lakoff and Nunez offers interesting insights into why humans find some mathematical concepts much more difficult than others. Other researchers, such as cognitive neuroscientist Rosemary Wiley of the University of Sheffield, suggest that at least some mathematical structures are parasitic on the language faculty. Mathematical insights developed by borrowing mind tools used for building language. The cognitive scientists make a fairly strong case for an association of our mathematics with the human mind and against Platonism. Interestingly, though what I regard as possibly the strongest argument against Platonism comes out from neurobiologists, but rather from Sir Michael Atiyah, one of the greatest mathematicians of the 20th century. I did, in fact, mention his line of reasoning briefly in chapter 1, but I would now like to present it in more detail. If you had to choose one concept of mathematics that has the highest probability of having a resistant dependence of the human mind, which one would you select? Most people would probably conclude that this has to be the natural numbers. What can be more natural than 1, 2, 3? Even the German mathematician of intuitionist inclinations, Leopold Kronecker, 1823 until 91, famously declared, God created the natural numbers, all as is the work of man. So, if one could show that even the natural numbers as a concept have their origin in the human mind, this would be a powerful argument in favor of an invention paradigm. Here again is how Atiyah argues that the case. Let us imagine that intelligence has resided not in mankind but in some vast solitary and isolated jellyfish buried up in the depths of the Pacific Ocean. It would have no experience of individual objects, only with the surrounding water. Motion, temperature, and pressure would provide its basic sensory data. In such a pure continuum, the discrete would not arise and there would be nothing to count. In other words, Atiyah is convinced that even a concept as basic as that of natural numbers was created by humans. By abstracting, the cognitive scientists would say, through grounding metaphors, elements of the physical world. Put differently, the number 12, for instance, represents an abstraction of a property that is common to all things that come in dozens in the same way that the word thoughts represents a variety of processes occurring in our brains. The reader might object to the use of the hypothetical universe of the jellyfish to prove this point. He or she may argue that there is only one inevitable universe and that very supposition should be examined in the context of this universe. However, this will be tantamount to conceding that the concept of natural numbers is in fact somehow dependent on the universe of human experiences. Note not that this is precisely what Lakoff and Nunez mean when they refer to mathematics as being embodied. I have just argued that the concepts of our mathematics originate in the human mind. You may wonder then why I had insisted earlier that much of mathematics is in fact discovered, a position that appears to be closer to that of the Platonists. Invention and discovery. In our everyday language, the distinction between discovery and invention is sometimes crystal clear, sometimes a bit fuzzier. No one would say that Shakespeare discovered Hamlet or that Madame Curie invented radium. At the same time, new drugs for certain types of diseases are normally announced as discoveries, even though they often involve the meticulous synthesis of new chemical compounds. I would like to describe in some detail a very specific example in mathematics, which I believe will not only help clarify the distinction between invention and discovery, but also yield valuable insights into the process by which mathematics evolves and progresses. In Book 6 of the Elements, Euclid's monumental work on geometry, we find a definition of a certain division of a line into two equal parts. An earlier definition in terms of areas appears in Book 2. According to Euclid, if a line AB is divided by a point C, figure 62, in such a way that the ratio of the length of the two segments AC CB is equal to the whole line divided the longer segment ABBC, then the line is said to have been divided in extreme and mean ratio. In other words, if AC BCB ABAC, then each one of these ratios is called the extreme and mean ratio. Since the 19th century, this ratio is popularly known as the golden ratio. Some easy algebra can show that the golden ratio is equal to. The first question you may ask is, why did Euclid even bother to define this particular line division and to give the ratio name? After all, there are infinitely many ways in which a line could be divided. The answer to this question can be found in the cultural, mystical heritage of the Pythagoreans and Plato. Recall that the Pythagoreans were obsessed with numbers. They thought of the odd numbers as being masculine and good, and rather judicially of the even numbers as being feminine and bad. They had a particular affinity for the number. They have a particular affinity for the number five, the union of two and three, the first even female, and the first odd masculine number. The number one was not considered to be a number, but rather the generator of all numbers. To the Pythagoreans, therefore, the number five portrayed love and marriage, and they used the pentagram, the five-pointed star figure 63, as the symbol of their brotherhood. Here is where the golden ratio makes its first appearance. If you take a regular pentagram, the ratio of the side of any one of the triangles is to its implied base A over B in figure 63 is precisely equal to the golden ratio. Similarly, the ratio of any diagonal of regular pentagon to its side CD in figure 64 is also equal to the golden ratio. In fact, to construct a pentagram using a straight edge and compass, the common geometrical construction process of the ancient Greeks requires dividing a line into the golden ratio. Plato added another dimension to the mythical meaning of the golden ratio. The ancient Greeks believed that everything in the universe is composed of four elements: earth, fire, air, and water. In Timaeus, Plato attempted to explain the structure of matter using the five regular solids, and now bears his name, the Platonic solids, figure 65. These convex solids, which include the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron, are the only ones in which all the faces of each individual solid are the same and are regular polygons, and where all the vertices of each solid lies on the sphere. Plato associated each of the Platonic solids with one of the four basic cosmic elements. For instance, the element, the Earth, was associated with a stable cube. the penetrating fire with the pointing tetrahedron, air with the octahedron, and water with the icosahedron. Concerning the dodecahedron, figure 65D, Plato wrote in Timaeus, as there still remain one compound figure, the fifth, God used it for the whole, bordering it with designs. So the dodecahedron represented the universe as a whole. Note, however, that the dodecahedron with its 12 pentagonal faces has the golden ratio written all over it. Both its volume and its surface area can be expressed as simple functions of the golden ratio. The same is true for the icosahedron. History therefore shows that by numerous trials and errors, the Pythagoreans and their followers discovered ways to construct the certain geometrical figures that to them represent important concepts such as love and the entire cosmos. No wonder then that they and Euclid, who documented this tradition, invented the concept of the golden ratio that was involved in these contractions and gave it a name. Unlike any other arbitrary ratio, the number 1.618 now become the focus of an intense and rich history of investigation, and it continues to pop up even today in the most unsuspected places. For instance, 2 millennia after Euclid, the German astronomer Johannes Kepler discovered that this number appears miraculously as it were in relation to a series of numbers known as the Fibonacci sequence. The Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233 is characterized by the fact that starting with the third, each number is the sum of the previous two, e.g. and so on. If you divide each number in the seconds by the one immediately preceding it, e.g., you find that the ratio oscillates about but come closer and closer to the golden ratio the farther you go in the sequence. For example, one obtains the following results rounding the numbers to the 6th decimal place, and so on. In more modern times, the Fibonacci sequence and concomitantly the golden ratio were found to figure the leaf arrangement of some plants, the phenomenon known as the phyllotaxis, and in the strata of the crystals of certain aluminum alloys. Why do I consider Euclid's definition of the concept of the golden ratio an invention? Because Euclid in fact invented the act, single this ratio, and attracted the attention of mathematicians to it. In China, on the other hand, where the concept of the golden ratio was not invented, the mathematical literature contains essentially no reference to it. In India, where again the concept was not invented, there are only a few insignificant theorems in trigonometry that peripherally involve this ratio. There are many that peripherally involve this ratio. There are many other examples that demonstrate that the question is mathematics as discovery or invention is ill-posed. Our mathematics is a combination of inventions and discoveries. The axioms of Euclid geometry as a concept were an invention, just as the rules of chess were an invention. The axioms were also supplemented by a variety of invented concepts, such as triangles, parallelograms, ellipses, the golden ratio, and so on. The theorems of Euclidean geometry, on the other hand, were, and by large discoveries, they were the paths linking the different concepts. In some cases, the proofs generated the theorems mathematicians examined that they could prove, and from that they deduced the theorems. In other words, as described by Archimedes in the method, they first found the answer to a particular question they were interested in, and then they worked out the proof. Typically, the concepts were inventions. primary numbers as a concept were an invention, but all the theorems about prime numbers were discoveries. The mathematicians of ancient Babylon, Egypt, and China were never invented the concept of prime numbers, in spite of their advanced mathematics. Could we say instead that they just did not discover prime numbers? Not any more than we could say that the United Kingdom did not discover a single codified documentary constitution. Just as a country can survive without a constitution, elaborate mathematics could develop without the concept of prime numbers. And it did. And it did. Do we know why the Greeks invented such concepts as the axioms and prime numbers? We cannot be sure, but we could guess that this was part of their relentless efforts to investigate the most fundamental constituents of the universe. Prime numbers were the basic building blocks of numbers, just as atoms were the building blocks of matter. Similarly, the axioms were the fountain for the fountain from which all geometrical truths were supposed to flow. The dodecahedron represented the entire cosmos, and the golden ratio was the concept that broke that symbol into existence. This discussion highlights another interesting aspect of mathematics. It is a part of the human culture. Once the Greeks invented the axiomatic method, all the subsequent European mathematics followed suit and adopted the same philosophy and practices. Anthropologist Leslie White, 1900 until 1975, tried once to summarize this cultural phase by noting: had Newton been read in Rotten Thought, South African tribal culture, he would have calculated like a Hottentot. This cultural complexion of mathematics is more probably responsible for the fact that many mathematical discoveries, e.g. of knot inference, and even some major inventions, e.g. of calculus, were made simultaneously by several people working independently. Do you speak mathematics? In a previous section, I compared the import of the abstract concept of a number to that of the meaning of a word. Is mathematics some kind of language, insights from mathematical logic on one hand and from linguistics on the other, so that to some extent it is. The work of Ball, Frege, Peano, Russell, Whitehead, Gödel, and the modern day followers, in particular in areas such as philosophical syntax and semantics, and in parallel in linguistics, have demonstrated that grammar and reasoning are intimately related to an algebra of symbolic logic. But why then are there more than 6,500 languages, while there is only one mathematics? Actually, all the different languages have many design features in common. For instance, the American linguist Charles F. Hockett, 1916 until 2000, drew attention in 1960s to the fact that all the languages have built-in devices for acquiring words and phrases. Think of homepage, laptop, indifferent, and so on. Similarly, all the human languages allow for abstraction, e.g. surrealism, absence, greatness, for negation, e.g. not, hasn't, and for hypothetical phrase, if grandma had wheels, she might have been a bus. Perhaps two of the most important characteristics of our languages are their open-endedness and their stimulus freedom. The former property represents the ability to create never-before-heard utterances and to understand them. For instance, I can easily generate a sentence such as, "You cannot repair the hover drum with chewing gum," and even though you have probably never encountered this sentence before, you have no trouble in understanding it. Stimulus freedom is the power of to choose how or even if one should respond to a received stimulus. For instance, the answer to the question posed by singer-songwriter Carole King in her song "Will You Still Love Me Tomorrow" could be any of the following: I don't know if I still be alive tomorrow. Absolutely, I don't even love you today, not as much as I love my dog. This definitely your best song. Or even I wonder who will win the Australian Open this year. You will recognize that many of these features, e.g., abstraction, negation, open-endedness, and the ability to evolve, are also characteristic of mathematics. As I noted before, Lakoff and Nunez emphasized that the role of metaphors in mathematics, cognitive linguistics, also argue that all human languages use metaphors to express almost everything. Even importantly, perhaps, ever since 1957, the year in which the famous linguist Noam Chomsky published his revolutionary work Syntax Structures. Many linguistic endeavors have revolved around the concept of a universal grammar, principles that govern all languages. In other words, what appears to be a Tower of Babel of diversity may really hide surprising structural similarity. In fact, if this were not the case, the dictionaries that translate from one language into another might have never worked. You may still wonder why mathematics is as uniform as it is, both in terms of subject matter and in terms of symbolic notation. The first part of discussion is particularly intriguing. Most mathematicians agree that mathematics as we know it has evolved from the basic branches of geometry and arithmetic that were practiced by the ancient Babylonians, Egyptians, and Greeks. However, was it truly inevitable that mathematics would start with these particular disciplines? Computer scientist Stephen Wolfram argued in his massive book, A New Kind of Science, that this was not necessarily the case. In particular, Wolfram said how starting from simple sets of rules that act as short computer programs known as cellular automata, one could develop a very different type of mathematics. These cellular automata could be used in principle at least as the basic tools for modeling natural phenomena instead of the differential equations that have dominated science for 3 centuries. What was it then that drove the ancient civilizations toward discovering and inventing our special brand of mathematics? I don't really know, but it may have had much to do with the straight lines and smooth curves very easily noticed, for instance. With what precision you can determine just by eye whether a line is perfectly straight or how effortlessly you are able to distinguish between a cycle and a shape that is slightly elliptical. These perceptual abilities may have strongly shaped the human experience of the world or may have therefore led to mathematics that was based on discrete objects, arithmetic, and on geometrical figures, Euclidean geometry. The uniformity in symbolic notation is probably a result of what one might call the Microsoft Windows effect. The entire world is using Microsoft's operating system not because this conformity was inevitable, but because once one operating system started to dominate the computer market, everybody had to adopt it to allow for ease in communication and for availability of products. Similarly, the Western symbolic notation is imposed uniformity on the world of mathematics. Intriguingly, astronomy and astrophysics may still contribute to the invention and discovery creation in interesting ways. The most recent studies of extrasolar planets indicate that about 5% of all stars have at least one giant planet like Jupiter in our own solar system revolving around them, and that this fraction remains roughly constant on the average all across the Milky Way galaxy. While the precise fraction of terrestrial of terrestrial Earth-like planets is not yet known. Chances that the galaxy is teeming with billions of such planets, even if only a small but not non-eligible fraction of these Earths are in the habitable zone. The rest of obvious that the loss of liquid matter of liquid water on planet's surface around their host, the probability of life in general and of intelligence in particular developing on the surface of these planets is not zero. If we were to discover another intelligent life from which we could communicate, we could gain invaluable information about the formalisms developed by this civilization to explain the cosmos. Not only would we make an unimaginable progress in understanding of the origin and evolution of life, but we could even compare our logic into the logical system of potentially more advanced creatures. On a much more speculative note, some scenarios in cosmology, e.g., one known as eternal inflation, predict the possible existence of multiple universes. Some of these universes may not only be characterized by different values of the constant of nature, e.g., the strength of the indifferent forces, the mass ratios of subatomic particles, but even by different laws of nature altogether. Astrophysicist Mark argues that there should even be a universe corresponding to, or that is, in his language, each possible mathematical structure. If this were true, this would be an extreme version of the universe. Is mathematics perspective, there is none, just one world that can identify with mathematics by the entire ensemble of them. Unfortunately, not only is this speculation radical and currently untestable, it also appears, at least in its simplest form, to contradict what has become known as the principle of mediocrity. As I have described in chapter 5, if you pick a person at random on the street, you have 95% chance that his or her height which would be within two standard deviations from the mean height. The similar argument will apply to the properties of universes. But the number of possible mathematical structures increases dramatically with increasing complexity. This means that the most mediocre structure close to the mean should be incredibly intricate. This appears to be at odds with the relative simplicity of our mathematics and our theories of the universe, thus violating the natural expectation that our universe should be typical. Next, enigma. In mathematics, is mathematics created or discovered? Is the wrong question to ask because it implies that the answer has to be one or the other and that the two possibles are mutually exclusive. Instead, I suggest that mathematics is partly created and partly discovered. Humans commonly invented mathematical concepts and discovered the relations among those concepts. Some empirical discoveries certainly preceded the formulation of concepts, but the concepts themselves undoubtedly provided an incentive for more theorems to be discovered. I should also note that some philosophers of mathematics, such as the American Hilary Putnam, adopt an intermediate position known as realism. They believed in the objectivity of mathematical discourse, that these sentences are true or false, and what makes them true or false is external to humans, without committing themselves, like the Platonists, to the existence of mathematical objects. Do any of these insights also lead to a satisfactory explanation for Wigner's and reasonable effectiveness puzzle? Let me first briefly review some of the potential solutions proposed by contemporary thinkers. Physics Nobel laureate David Gross writes, A point of view that, from my experience, is not uncommon among creative mathematics, namely that mathematical structures that they arrive at are not artificial creations of the human mind, but rather have naturalness to them, as if they were as real as the structures created by physicists to describe the so-called real world. Mathematicians, in other words, are not inventing new mathematics, they are discovering it. If this is the case, then perhaps some of the mysteries that we have been exploring, the unreasonable effectiveness, are rendered slightly less mysterious. If mathematics is about structures that are a real part of the natural world, as real as the concepts of theoretical physics, then it is not so surprising that it is an effective tool in analyzing the real world. In other words, Gauss relies here on a version of the mathematics as a discovery perspective that is somewhere between Platonic world and the universe is mathematics world, but closer to a Platonic viewpoint. As we have seen, however, it is difficult to philosophically support the mathematics as a discovery claim. Furthermore, Platonism cannot truly solve the problem of the phenomenal accuracy that I have described in chapter 8, a point acknowledged by Gauss, Sir Michael Atiyah, who whose views on the nature of mathematics I have largely adopted, argues as follows. If one views the brain in its evolutionary context, then the mysterious success of mathematics in the physical sciences is at least partially explained. It has been evolved in order to deal with the physical world, so it should not be too surprising that it has developed a language, mathematics, that is well suited for the purpose. The line of reasoning is very similar to the solutions proposed by the cognitive scientists. Atiyah also recognizes, however, that this explanation narrowly addresses the thornier parts of the problem. How does mathematics explain the more esoteric aspects of the physical world? In particular, this explanation leaves the question of what I call the passive effectiveness. Mathematical concepts finding applications long after their invention entirely open. Atiyah notes, the skeptic can point out that the struggle for survival only requires us to cope with physical phenomena at the human scale, yet mathematical theory appears to deal successfully with all scales from the atomic to the galactic, to which his only suggestion is, perhaps the explanation lies in the abstract hierarchical nature of mathematics, which enable us to move up and down the world scale with comparative ease. The American mathematician and computer scientist Richard Hamming, 1915 until 89, and 1915 until 98, provided a very extensive interesting discussion on Wigner's enigma in 1980. First, on the question of the nature of mathematics, he concluded that mathematics has been made by man and therefore is apt to be altered rather continuously by him than he possessed for potential explanations for unreasonable effectiveness. 1. Selection effects. 2. Evolution of the mathematical contours. 3. The limited explanatory power of mathematics. And 4. Evolution of humans. We call the selection effects are distortions introduced in the results of experiments, either by apparatus being used or by the way in which the data are collected. For instance, if in a test of the efficiency of a dieting program, the researcher would reject everyone who drops out of the trial, this would bias the result, since most likely the ones who drop out are those for whom the program wasn't working. In other words, Hamming suggests that at least in some cases, the original phenomenon arises from the mathematical tools we use and not from the real world. A lot what we see comes from the glasses we put on. As an example, he correctly points out that one can saw that any force symmetrically emanating from a point and conserving energy in three-dimensional spaces three-dimensional space should behave according to an effects quite low, and therefore that the applicability of Newton's law of gravity should not be surprising. Hamming's point is well taken, but selection effects can hardly explain the fantastic accuracy of some theories. Hamming's second potential solution relies on the fact that the human select and continuously improve the mathematics to fit a given situation. In other words, Hamming proposes that we are witnessing what we might call an evolution and natural selection of mathematical ideas. Humans invent a large number of mathematical concepts, and only those that fit are chosen. For years, I also used to believe that this was the complex explanation. A similar interpretation was proposed by physical Nobel laureate Steven Weinberg in his book Dreams of a Final Theory. Can this be the explanation to Wiener's enigma? There is no doubt that such selection and evolution occur. After shifting to a variety of mathematical formalisms and tools, scientists retain those that work, and they do not hesitate to upgrade them or change them as better ones become available. But even if we accept this idea, why are there mathematical theories that can explain the universe at all? Hamming's third point is that our impression of the effectiveness of mathematics may, in fact, be an illusion, since there is much in the world around us that mathematics does not really explain. In support of this perspective, I could note, for instance, that the mathematician Israel Moshevich's girlfriend was once quoted as having said, there is only one thing which is more unreasonable than the unreasonable effectiveness of mathematics in physics, and this is the unreasonable ineffectiveness and persist aided of mathematics in biology. I do not think that this in itself can explain away Wiener's problem. It is true that unlike in the Hitchhiker's Guide to the Galaxy, we cannot say that the answer to life, the universe, and everything is 42. Nevertheless, there is a sufficiently large number of phenomena that mathematics does elucidate to warrant explanation. Moreover, the range of facts and processes that can be interpreted by mathematics continually widens. Hamming's third explanation is very similar to the one suggested by Atiyah, that Darwinian evolution would naturally select for survival those competing forms of life which had the best models of reality in their minds. Best meaning best for surviving and propagating. Computer scientist Jeff Ruskin, 1843 until 2005, who started the Macintosh project for Apple Computer, also had related views with a particular emphasis on the role of logic. Ruskin concluded that human logic was forced on us by the physical world and is therefore consistent with it. Mathematics derives from logic. This is why mathematics is consistent with the physical world. There is no mystery here, though we should not lose our sense of wonder and amazement at the nature of things even as we come to understand them better. Hamming was less convinced even by the strength of his own argument. He pointed out that if you pick 4,000 years for the age of science, generally that you get an upper bound of 200 generations. Considering the effects of evolutions, we are looking for via selection of small chance variations. It does not seem to me that evolution can explain more than a small part of the reasonable effectiveness of mathematics. Ruskin insisted that the groundwork for mathematics had been laid down long before in our ancestors, probably over millions of generations. I must say, however, that I do not find this argument particularly convincing. Even if logic had been deeply embedded in our ancestors' brains, It's difficult to see how this ability could have led to abstract mathematical theories of the subatomic world, such as quantum mechanics, that display stupendous accuracy. Remarkably, Hamming concluded his article with an admission that all of the explanations I have given when added together simply are not enough to explain what I set out to account for, namely the unreasonable effectiveness of mathematics. So we close by conceding that the effectiveness of mathematics remains as mysterious as it was when we started. Before giving up, let us try to distill the sense of Wiener's puzzle by examining what is known as the scientific method. Scientists first learn facts about nature through a series of experiments and observations. Those facts are initially used to develop some sort of qualitative models of the phenomena, e.g. the Earth attracts apples, colliding subatomic particles can produce other particles, the universe is expanding, and so on. In many branches of science, even the emerging theories may remain non-mathematical. One of the best examples of a powerful explanatory theory of this type is Darwin's theory of evolution. Even though natural selection is not based on a mathematical formalism, its success in clarifying the origin of species has been remarkable. In fundamental physics, on the other hand, usually the next step involves attempts to construct mathematical quantitative theories, e.g. general relativity, quantum electrodynamics, string theory, and so on. Finally, the researchers use those mathematical models to predict new phenomena, new particles, and results of never before performed experiments and observations. What puzzled Wiener and Einstein was the incredible success of the rush to possess. How is it possible that time after time, physicists are able to find mathematical tools that not only explain the existing experimental and observational results, but which also led to entirely new discernments and new predictions? I attempt to answer this version of the question by borrowing a beautiful example from mathematician Raven has proposed that in the spirit of the analysis of many such problems in mathematics and indeed in theoretical physics, one should examine the simplest possible case. Consider the seemingly trivial experiment of putting pebbles into an opaque vase. Suppose you first put in four. Suppose you first put in four red pebbles and later you put in 7 black pebbles. At some point in their history, humans learned that from some purposes they could represent a collection of pebbles of any color by an abstract concept that they had invented a natural number. That is, the collection of white pebbles could be associated with the number 4 or whichever symbol was used at the time, and the black pebbles with the number 7. Via experimentation of the type 1 have described above, humans also discovered that another invented concept, arithmetic addition, represents correctly the physical act of aggregation. In other words, the result of the abstract process denoted symbolically by 4, 7 can predict unambiguously the final number of pebbles in the vase. What does all of this mean? It means that humans have developed an incredible mathematical tool, one that could reliably predict the result of any experiment of this type. This tool is actually much less trivial than it might seem, because the same tool, for instance, does not work for drops of water. If you put 4 separate drops of water into phase, followed by 7 additional drops, you don't get 11 separate drops of water in the phase. In fact, to To make any kind of prediction for similar experiments with liquids or gases, humans had to invent entirely different concepts such as weight, and to realize that they have to weigh the individual each drop of volume of gas. Each drop of volume of gas. The lesson here is clear. The mathematical tools were not chosen arbitrarily, but rather precisely on the basis of their ability to correctly predict the results of the relevant experiments or observations. So, at least for this very simple case, their effectiveness was essentially guaranteed. Humans did not have to guess in advance what the correct mathematics would be, nor to afford them the luxury of trial and error to determine what worked. They also did not have to stick with the same tools for all circumstances. Sometimes the appropriate mathematical formalism for a given problem did not exist, and someone had to invent it, as in the case of Newton inventing calculus or modern mathematicians inventing various topological geometric ideas in the context of the current efforts in string theory. In other cases, the formalism had already existed, but someone had to discover that this was a solution awaiting the right problem, as in the case of Einstein using Riemannian geometry or particle physicists using group theory. The point is that through a burning curiosity, stubborn persistence, creative imagination, and fierce determination, humans were able to find the relevant mathematical formalisms for modeling a large number of physical phenomena. One characteristic of mathematics that was absolutely crucial for what I dubbed the passive effectiveness was its essential eternal validity. Euclidean geometry remains as correct today as it was in 300 BC. We understand now that its axioms are not inevitable, and rather than representing absolute truths about space, they represent truths within a particular human perceived universe and its associated human invented formalism. Nevertheless, once we comprehend the more limited context, all the theorems hold true. In other words, branches of mathematics get to be incorporated into larger, more comprehensive branches, e.g. Euclidean geometry is only one possible version of geometry, but the correctness within each branch persists. It is this indefinite longevity that has allowed scientists at any given time to search for adequate mathematical tools in the entire arsenal of developed formalisms. The simple example of the pebbles in the vase still does not address the elements of Vineyard's enigma. First, there is the question why in some cases do we seem to get more accuracy out of the theory that we have put into it. In the experiment with the pebbles, the accuracy of the predicted results, the aggregation of other numbers of pebbles, is not any better than the accuracy of experiments that had led to the formulation of theory arithmetic addition in the first place. On the other hand, in Newton's theory of gravity, for instance, the accuracy of its predictions proved to far exceed that of the observational results that motivated the theory. Why a brief examination of the history of Newton's theory may provide some insight. Ptolemy's geocentric model reigned supreme for about 15 centuries. While the model did not claim any universality, the motion of each planet was treated individually, and there was no mention of physical causes, e.g. forces, acceleration. The agreement with observations was reasonable. Nicolaus Copernicus, 1473 until 1543, published his heliocentric model in 1543, and Galileo put it on solid ground, so to speak. Galileo also established the foundation for the laws of motion, but it was Kepler who deduced from observations the first mathematical, albeit only phenomenological, laws of planetary motion. Kepler used a huge body of data left by astronomer Tycho Brahe to determine the orbit of Mars. He referred to the ensuing hundreds of sheets of calculations as my warfare with Mars, except for two discrepancies. A circular orbit matched all the observations. Still, Kepler was not satisfied with this small solution, and he later described his thought process. If I had believed that if we could ignore these 8 minutes, if those 8 minutes of arc about a quarter of the diameter of a full moon, I would have patched up my hypothesis accordingly. Now, since it was not permissible to disregard those 8 minutes, also pointed to path to a complex reformation in astronomy. The consequences of this meticulousness were dramatic. Kepler inferred that the orbits of planets are not circular but elliptical, and he formulated two additional quantitative laws that apply to all planets. When these laws were coupled with Newton's laws of motion, they serve as the basis for Newton's law of universal gravitation. Recall, however, that along the way Descartes proposed his theory of vortices, in which planets were carried around the sun by vortices of circularly moving particles. This theory could not get very far, even before Newton sought it to be inconsistent, because Descartes never developed a systematic mathematical treatment of his vortices. What do we learn from this concise history? There can be no doubt that Newton's law of gravitation was the work of a genius, but this genius was operating in a vacuum. Some of the foundations had been painstakingly laid down by previous scientists. As I noted in chapter 4, even much lesser mathematicians than Newton, such as the architect Christopher Wren and the physicist Robert Hooke, independently suggested the first square law of attraction. Newton's greatness showed in his unique ability to put it all together in the form of a unifying theory, and in his insistence on providing a mathematical proof of the consequences of his theory. Why was this formalism as accurate as it was? Partly because it treated the most fundamental theorem, the forces between the two gravitating bodies and the resulting motion. No other complicating factors were involved. It was for this problem and this problem alone that Newton obtained a complete solution. Hence, the fundamental theory was extremely accurate, but its implications had to undergo continuous refinement. The solar system is composed of more than two bodies. When the effects of the other planets are included, still according to the first square law, the orbits are no longer simple ellipses. For instance, the Earth's orbit is bound to slowly change its orientation in space, a motion known as precession, similarly to that exhibited by the axis of a rotating top. In fact, modern studies have shown that, contrary to Laplace's expectations, the orbit of the planets may eventually even become chaotic. Newton's fundamental theory itself, of course, was later subsumed by Einstein's general relativity, and the embarks of the theory also follow a series of false starts and never misses. So, the accuracy of a theory cannot be anticipated. The proof of the pudding is in the eating. Modifications and amendments continue to be made until this desired accuracy is obtained. Those few cases in which a superior accuracy is achieved in a single step have the appearance of miracles. There is clearly one crucial fact in the background that makes the search for fundamental laws worthwhile. This is the fact that nature has been kind to us by being governed by universal laws rather than by mere parochial laws. A hydrogen atom on Earth at the other edge of the Milky Way galaxy, or even in a galaxy that is 10 billion light years away, behaves in precisely the same manner. And this is true in any direction we look at and at any time. Mathematicians and physicists have invented a mathematical term to refer to such properties There are cosymmetries and they reflect immunity to change in location, orientation, or the time you start your clock. If not for this and another symmetries, any hope of ever disappearing nature can decide would have been lost, since experiments would have had to be continuously repeated in every point in space if life could emerge at all in such an universe. Another feature of the cosmos that lurks in the background of mathematical theories has become known as locality. This reflects our ability to construct the big picture like a jigsaw puzzle, starting with a description of the most basic interactions among elementary particles. We now come to the last element in Wiener's puzzle. What is it that guarantees that a mathematical theory should exist at all? In other words, why is there, for instance, a theory of general relativity? Could it not be that there is no mathematical theory of gravity? The answer is actually simpler than you might think. There are indeed no guarantees. There exists a multitude of phenomena for which no precise predictions are possible, even in principle. This category includes, for example, a variety of dynamic systems that develop chaos, where the tiniest change in the initial conditions may produce entirely different end results. Phenomena that may exhibit such behavior include the stock market, where the pattern above the Rocky Mountains, a ball bouncing on a roulette wheel, the smoking rising from a cigarette, and indeed the orbits of the planets in the solar system. This is not to say that mathematicians have not developed indigenous formalisms that can address some important aspects of these problems, but no deterministic predictive theory exists. The entire fields of probability and statistics have been created precisely to tackle those areas in which one does not have a theory that yields much more than what has been put it. Similarly, a concept dubbed computational complexity delineates limits to our ability to solve problems by particle algorithms and Gödel's incompleteness theorems mark certain limitations of mathematics even within itself. So mathematics is indeed extraordinarily effective for some descriptions, especially those dealing with the fundamental science, but it can describe our universe in all its dimensions. To some extent, scientists have selected what problems to work on based on, the, on those on those problems being amenable to a mathematical treatment. Have we then solved the mystery of the effectiveness of mathematics once and for all? I have certainly given it my best shot, but I doubt very much that everybody would be utterly convinced by the arguments that I have articulated in this book. I can, however, cite Bertrand Russell in The Problem of Philosophy. Thus, to sum up our discussion of the value of philosophy, philosophy is to be studied not for the sake of any definite answers to its questions, since no definite answer can, as a rule, be known to be true, but rather for the sake of the questions themselves, because these questions enlarge our conception of what is possible, enrich our intellectual imagination, and diminish the dogmatic assurance which closes the mind against speculation, but above all because through the greatness of the universe which philosophy contemplates, the mind is also rendered great and becomes capable of the union with the universe which constitutes its highest good.